Good morning. Today I am going to explain the applications of Gauss law. This is one of the important topic in electric charges and fields. The first application is expression for intensity of electric field due to uniformly charged cylinder. Here we have to consider the two situations or two cases. When the point P is lies inside the cylinder, what will be the electric field intensity, and when the point is lies outside the cylinder, what will be the electric field intensity. So now for that purpose, let us consider a long, infinitely long cylinder, and that cylinder having a radius R, capital letter R, okay, and this cylinder is uniformly charged, okay. Now here the a point P is lies inside the cylinder, where we have to calculate the intensity of electric field at a point P. Now from this point P, we have to draw a coaxial cylinder, okay, whose length is L and whose radius is small letter r, okay. Now we have to calculate the total electric field through this coaxial cylinder. So because of this coaxial the electric field, we have to calculate the electric field through the curved surface and the electric field through the two caps, okay. So here for that purpose I have wrote that few points about this. Let us consider an uniformly charged cylinder with radius r, okay. So this is uniformly charged cylinder with radius capital letter r. Let P be any point inside the cylinder, okay. First of all we have to consider, let P be any point inside the cylinder at a distance of r from the axis. This point P is at a distance of r from the main axis, okay. Now the total draw a coaxial cylinder with a radius r. We have to draw a coaxial cylinder with radius r, okay. Now the total electric flux through the coaxial cylinder is the sum of electric flux through due to the curved surface and the electric flux due to the caps. So just now I told you that is the total electric flux through this coaxial cylinder will be the electric flux through the curved surface and the electric flux through the two caps, okay. But here the electric flux due to the caps is 0, because here the cos theta is exactly 90 degrees. That is the angle between the electric field and the surface area will be 90 degrees. But here the along the curved surface, you can see this is a surface area and the electric field is parallel, so that's why cos theta will be 1. Here the cos theta is 0, okay. So that's why we have to neglect, or we have to cancel the electric field through the two caps. Then we have to take only the electric field through the this curved surface, okay. So that point only I wrote. But here the flux electric flux due to the caps is 0, because theta is 90 degrees. So that electric flux due to the curved surface can be taken as, so curved surface, generally we can write electric flux is nothing but it's a product of electric field into area. So electric field into area, here the area of the cylinder or curved surface will be, can be written as, cylinder area will be, that is 2 pi RL, okay. So I wrote the area of the cylinder is 2 pi RL. Let us take that is equation number 1. Now here the charge is what? Q is equal to rho into V, we know this one. So here V is the volume of the only curved surface, okay. So curved surface volume can be written as pi R square L. Let us take that is equation number 2. Now according to the Gauss law, we know that phi E, the electric flux through a closed surface, will be equal to the Q by epsilon naught, the charge enclosed by the surface by permeability constant. So now here we have to substitute the equation number 2 in equation number 1. So we can write from equation number 1 and 2, we can write here E phi B value is E into 2 pi RL, and that charge is Q in rho into pi R square L by epsilon naught is as it is. So E can be written as rho by 4 2 pi RL into pi r square L by epsilon naught. So RR get cancelled, pi pi LL get cancelled, then we get E is equal to rho R by 2 epsilon naught is the electric field due to the uniformly distributed charge cylinder at a point P. Electric field at a point P due to the uniformly charged sphere. Okay. Now we have to consider the situation when the point P is lies outside the cylinder. Here the situation will be like this. So when the point is lies outside the cylinder as shown in the figure, here that time here again we have to consider the coaxial cylinder, or we can draw the coaxial cylinder. Again the electric flux through these caps will be 0 because the angle between the E and ds is 90 degrees, that is ds cos theta is nothing but 90 degrees. So that's why we can take cos 90 is 0. So the electric flux through these two caps will be 0. Then we have to consider the electric flux through the curved surface only. Okay, so here again we have to consider the situation. Let us consider a uniformly charged cylinder with radius r. Again this is the main cylinder. So this cylinder is uniformly charged whose radius is r, capital letter R. Now let P be any point on the outside the cylinder at a distance of r. Here P be any point. Here the point P is here. P is a point which is outside the cylinder. Okay. Now draw a, and this is P is also at a distance of r, that is small letter r. Now draw a coaxial cylinder with radius r and length L. Okay. Now from this we have to draw a coaxial cylinder whose length is r. Okay. Now here we can write the electric flux through the coaxial cylinder. Same, that is phi E is equal to E cross area. We know this one. Now phi is equal to E into area of the coaxial cylinder. Area of that one is 2 pi RL. Next, charge can be written as rho into V. So volume of the cylinder, coaxial cylinder, is pi r square L. Now from equation number 1 and 2 we can write according to the Gauss law, phi E is equal to Q by epsilon naught. So we can write, if you cancel these terms, then E is equal to rho r square by 2 r epsilon naught. Okay. Thank you. For more videos, subscribe my channel Physics.